All right, so today we're going to start discussing our logic unit, right? And so the idea behind this is that everything in mathematics follows a very sequential order, right? One thing leads to the next. And so it introduces a very logical, sequential thought process. Knowing this, I can conclude this kind of a thing, right? And there's two different ways that we can approach that, two different ways of thinking that would get us to conclusions and whatnot. There's inductive reasoning and deductive reasoning, and we're going to focus on inductive reasoning today. So we're going to use inductive reasoning to help establish a pattern and make some conjectures. As a matter of fact, that's exactly what inductive reasoning is. Now, through a lot of this, there's going to be a lot of definitions to write out, so at any time, feel free to stop the video and finish writing out the definitions and then start it back up to hear some of the explanation behind it, right? But inductive reasoning is the process of observing data and recognizing patterns. And we're going to recognize those patterns and then make generalizations about society or about a thing or a group or whatever. That's called inductive reasoning. We're using patterns to try to come up with predictions or conjectures, which is our next definition, right? We're going to use patterns to come up with a conjecture. This is what we believe to be true based on what we've seen so far. And so a conjecture is a generalization made from using inductive reasoning, all right? Conjectures aren't always true, but they're true for as far as we can tell. And they'll be true all the way up until the point where we can find a counterexample. So I recognize a pattern, I'm going to establish a belief system, and I'm going to believe that up until someone can show me a counterexample to prove me wrong, right? And so a counterexample is a specific case for which the conjecture is false. For example, from every movie that I've seen, every cartoon that I've watched, I'm a 6-year-old, right? And every apple has been red so far. So I decide that all apples are red. And so I now believe that all apples are red. Well, is that true? Are all apples red? No, definitely not. We know that there are green apples, Granny Smith apples, there are green apples, and there are yellow apples. And so there are other colored apples out there. So in order to move myself from that belief system, I would need someone to come up with that counterexample. Here's a green apple. Obviously not all apples are red. Okay? All right. So trying to make a conjecture, another example here in more of a scientific setting. Right, so a scientist dips a platinum wire into a solution containing salt, sodium chloride, passes the wire over a flame, and observes that it produces an orange-yellow flame. She does this with many other solutions that contain salt, finding that they all produce an orange-yellow flame. So, make a conjecture. If you were doing this, what generalization would you make? What conclusion would you reach? What do you think? Well, if you've done this over and over again, then hopefully one thought you would have is, okay, well apparently all salt solutions or all sodium chloride solutions produce an orange-yellow flame. That's what we've seen, right? Now, I kind of like to argue this. You could also use the fact that the scientist keeps using a platinum wire, and so maybe platinum produces an orange-yellow flame. But anyway, sodium chloride produces an orange-yellow flame. Now, that's a conjecture. Do we know that that's true? Has she tried every possible sodium chloride solution to make sure that that works? No, but she's done it enough that she's starting to see a pattern develop to make that conjecture and feel comfortable that that's true. Someone would need to come up with a counterexample, a sodium chloride solution that does not produce an orange-yellow flame to make her believe something different, right? Come up with a counterexample. All right? So that's one type of inductive reasoning. Another type is, in a more mathematical setting, take a set of numbers and try to come up with the next two in the sequence. And we've got that kind of example here. Now, we also want to be able to explain the pattern that you're using, right? When we start dealing with numbers and sequences of numbers, the pattern may not be quite so obvious for everyone else, so we have to be able to explain it. That's going to be the difficult part here. Take a second, come up with the next couple of numbers in each sequence, and then try to write out an explanation of that pattern. And I'll walk you through that in a second, and you can kind of clean it up if you need to. But stop the video and give that a shot. Okay? The first one, did you come up with the two numbers 16 and 22? Because if you take a look at the difference between each consecutive number, that difference goes up by 1, right? So from 7 to 11, it goes up by 4. From 11, we need to go up 5 to get us to our 16, and then continuing to use that pattern, we're going to go up 6 from 16 to get 22. And so explain that pattern. Well, this is hard, but one thing you can say is the difference between consecutive numbers increases by 1. Okay? Now the next pattern, right? Hold, please. Okay, so the next one, did you recognize the fact that you could create common denominators for each of these fractions? And if you do, then it becomes a bit easier to see what's going on, right? And we can see that we're going to add 1/6 each time. And so the next two numbers become 5/6 and 1. And so coming up with the pattern there just simply says we're going to add 1/6 to each number. Okay? Another way to use patterns to make a conjecture is to take some data and display it in a graph and then try to make a conjecture that way. Okay? So take a look at this graph for a second. We've got a multiple choice question here. And see which choice seems to make the most sense. Stop the video, think about it for a second, look at the choices and come up with what you think. Okay, hopefully based on the graph, B makes the most sense, right? More girls are playing soccer today than in 1995, right? Even if today, and today being like 2013, out here, you would anticipate by the pattern that the number of girls playing would continue to increase, and so end up being someplace up here. And 95 is all the way down here. Now, you can go through the other choices. More boys play soccer than girls. Well, this graph has absolutely nothing to do with boys playing soccer. So that's not it. More people are playing soccer today than in the past because the 94 World Cup games were held in the U.S. Well, this graph doesn't say anything about the World Cup games. And it doesn't just say people. It talks about girls. So that's out. And then D, the number of girls playing soccer was more in 95 than in 2001. That's just plain wrong. So B ends up being the choice, right? So again, using patterns to establish conjectures. And again, those conjectures would be true until we come up with a counterexample. Okay? That leads us into conditional statements. If we believe these conjectures to be true, then we would start writing some of these statements into conditional statements. And so we'll talk about those and how to create those conditional statements next. Right? So first of all, a conditional statement is a logical statement that has two parts. It has a hypothesis and a conclusion. If this is going to happen, then this will happen. There's a condition put on this conjecture, right? This is only going to be true as long as something happens first, right? And I mentioned if and then, and that's the form that these conditional statements will take, the if-then form. The hypothesis will be the if. If this particular thing is true, then the next thing will be true, and that's your conclusion. The then will be your conclusion. Okay? Again, more definitions that you have to write down, so feel free to stop the video and then get it going again once you have everything written down. Okay? All right, so take a stab at writing a conditional statement, right? Here's one, and I'll walk you through it, right? If we know that the car runs when there is gas in the tank. So the hypothesis is your condition. What has to be true first to make something else happen? And the sentence says again, the car runs when there is gas in the tank. Well, that's your condition, when there is gas in the tank. So to rewrite this in a conditional if-then form, we'd want to say, if there is gas in the tank, then the car will run. Now, whether or not it's true is completely separate, right? Some if-then statements are going to be true, some of them are going to be false. It doesn't matter, we still need to write them. So don't get too hung up with whether a statement is true or false that you're writing, right? As a matter of fact, we can talk about it. If there's gas in the tank, then the car will run. Is that true or false? Well, obviously this is false. There are plenty of cars that have gas in the tank that do not run. They have other mechanical issues or whatever. So that's going to be a false statement, right? How about this one? Try writing the conditional statement for there are 12 eggs if the carton is full. Go ahead and write your statement. Start the video back up and see if you came up with the right statement. Did you write? If the carton is full, then there are 12 eggs. This one was a little bit easier to pick out because the word if was in the original statement. Okay? All right. Now, there are other, so from a if-then statement, from a conditional if-then statement, we can create other if-then statements by moving those pieces around. And when we create our new if-then statements, some of those will be true and some of those will be false. Right? And so we'll continue to talk about that, but as you move pieces around, you can change the meaning of the sentence. So we first talk about the negation. The negation of an if-then statement, or the negation of a statement, is a statement that is the opposite of the original statement, right? We can go back to this. If the carton is full, the negation of that hypothesis would be if the carton is not full. So basically using the word not to create the opposite. Okay? So, for example, conditional statement, if I earn enough money, then I can buy a Porsche. Okay? That's true enough. If we were to create the converse, right? The converse is what we get when we just switch the hypothesis and the conclusion. So this guy would go here and this guy would go there. So in other words, if I can buy a Porsche, then I earned enough money. Right? That's your converse. Is that true? If I can buy a Porsche, then I earned enough money? We can always argue semantics. What do you mean by earn? If someone gives you the money, then you're not earning it. But anyway, I think that was true in the true spirit of what we're trying to do here. Okay? But that's the converse. The inverse comes from negating the hypothesis and the conclusion of the original if-then, right? So if not the hypothesis, then not the conclusion, right? In other words, just not the original if part. So if I do not earn enough money, and I'll just say earn, then I cannot buy blah, blah, blah. And that's true enough as well. If I do not earn enough money, then I cannot buy a Porsche. Okay? So just take the original if-then and negate both parts. The contrapositive is created by taking the converse and negating that, right? So switch it and negate the statements. So in other words, switch first. I can buy a Porsche and then negate it. If I cannot buy a Porsche, then I did not earn enough money, blah, blah, blah. And that is not necessarily true either. That could be false, right? There could be other reasons why you didn't buy the Porsche, other than you did not earn enough money. So, again, don't get too wrapped up in true-false with these statements. Just write the statements, and then we can determine if they're true or false. It's perfectly fine to have a false if-then. Okay? All right. So now you give it a shot, right? Write an if-then statement, and then come up with the converse, the inverse, and the contrapositive. Take a second to write the original if-then, and then we'll agree on that, and then write the converse, inverse, and contrapositive. Did your original if-then look like this? If you are a soccer player, then you are an athlete. It doesn't have to be word for word the exact same thing, but it should be pretty close. Okay? Now, write the converse, the inverse, and the contrapositive. Again, stop the video, write those out, start them back up, and we can see what those statements should look like. Okay? The converse, we're going to switch the hypothesis and the conclusion. So now we're going to say, if you are an athlete, then you are a soccer player. Right? We didn't do true-false on the first. So if you are a soccer player, then you are an athlete. I think that's false. I'm sorry. I think that's true. I think that's fair enough to say that if you're playing soccer, then you're probably an athlete. The converse, if you are an athlete, then you are a soccer player. Well, that's false, right? You can definitely be an athlete and play some other sport. It doesn't have to be soccer, right? The inverse should look something like, now we're going to negate the original if-then statement. If you are not a soccer player, then you are not an athlete. Okay? And then again, I think the inverse is false, because you could definitely not be a soccer player but still be an athlete, just play a different sport. Same reason for the converse. The contrapositive should look like this. Take the converse and negate it. If you are not an athlete, then you are not a soccer player. Okay? And that's true enough, I think. It would be very difficult to play soccer if you were not an athlete. All right? All right. Hopefully that makes enough sense. We've got one last thing to talk about here, and that's biconditional statements, right? A biconditional statement happens if the original if-then statement and its converse are both true. In other words, if you flip-flop the hypothesis and the conclusion from an if-then that's true, then you still get a statement that's true. So it doesn't matter what happens first, basically, is what that means, right? That becomes what we call a biconditional statement. Two ways. It can go two ways, right? And in a biconditional statement, we'll join the hypothesis and the conclusion, which now can be switched either way, with the words if and only if. We'll take if then out and put if and only if in. Okay? Now your notes may differ a little bit here, but if you were, and here's what we mean. Right? We may have the conditional statement that if two lines intersect to form a right angle, then they are perpendicular, and that's true. The converse is also true. If two lines are perpendicular, then they intersect to form a right angle. That would lead us to say, so since both of these are true, it doesn't matter which one comes first, then we can write the biconditional statement, take the if and the then out of here, and join those two parts with if and only if. So two lines perpendicular, and that's the symbol for perpendicular. Two lines are perpendicular if and only if, and that's the abbreviation for if and only if. IFF is the abbreviation for if and only if. They intersect to form a right angle. Okay? So that's what we mean by a biconditional statement. The converse and the original statement are true, so we take the if and the then out. We don't really establish a hypothesis and a conclusion, and we take those two parts and join them with if and only if. Okay? All right, that's it. Homework's out in Canvas. Make sure you have that done next time.